All right. Hello, everyone, and thank you for attending today's webinar, Models That Work, Achieving Building Retrofits at Scale. Today, we'll be discussing several approaches for decarbonizing buildings, focusing on specific technologies, case studies, and financing and implementation approaches. My name is Heather Goach, and I will be your moderator today. Before we begin, there are a few housekeeping announcements that I think you're probably all familiar with. As you know, this screen is customizable, so feel free to make the various windows as large or small as you would like. You can even minimize them to drop to the menu at the bottom of your screen and click through the widgets at the bottom of the screen to be sure you aren't missing any options that are available. Presentations are also available to be downloaded as PDFs from the presentation list in the menu. Attendees are also in listen-only mode, but can submit questions through the Q&A box at any time during the webcast. The presenters will respond to questions at the end of the presentations, and the Q&A can be accessed in the menu at the bottom of your screen if it's not already available or visible. All presentations will also be available for on-demand viewing within a few days on the Engagement Hub. Later this afternoon, after the panel sessions, informal sessions and social times will be offered through Zoom links. And we will be having one for this session from 4:30 to 5:30. So to access these sessions, you'll find the links in the session icons on the menu bar. And on behalf of ACEEE, we wish to first recognize and thank our sponsors for this event. And make sure that we're moving through these. Bear with me for a second. Okay, so again, we thank our gold sponsors, as you can see here. Our silver sponsors, and our bronze. And with that, so I would like to introduce our distinguished panel of speakers. They are Robert Greenwald, President of Prism Engineering, and he will be presenting on the deep carbon retrofit strategies for commercial buildings. Jean-Philippe Hardy, who's a senior consultant with Dunsky Energy Consulting, and Jareen Ahmed, senior engineer with Southern California Edison's Emerging Products Group. Okay, so with our first speaker, who is a professional engineer and is based in Vancouver, Canada, where he leads the firm Prism Engineering, sorry about that. He is a proverbial expert in the field of commercial and industrial retrofits, where he has focused his 30-year career. He's conducted hundreds of energy audits, completed numerous retrofits and energy management plans, and facilitated over 200 energy management workshops. Robert Greenwald will discuss strategies and case studies for retrofits to commercial buildings. So Robert, it's all yours.
Much, Heather. Appreciate the introduction, and thanks for everyone for coming on the third or maybe the fourth day for you to the conference. It's amazing to think that it was only a year ago that I was in Portland for the industrial summer study, and it feels like a lot longer than that. Today, I plan to share with you sort of the concepts of deep retrofits and how we see that in our area. Geography-wise, I'm going to be sharing with you studies from British Columbia, north of the border. And we'll also be sharing lessons learned and considerations for deep retrofits. I'm happy to be able to launch a poll question. I know you haven't seen these too often. It's only the second time in the conference to do so, but I really miss the personal interactions myself of these conferences when we're going virtual. And so you now have a chance to be part of the presentation. So I like your definition of a deep retrofit. I heard earlier this week from David Jump at KW Engineering a definition of deep retrofits greater than 10% savings. Do you feel that it's I'm going to choose A if it's 20% or more, B 33% or more, C 50% or more, D 75% or more savings or reduction, and E 100% reduction or net zero? Of course, I haven't defined yet whether it's energy or carbon, but let's just go with deep retrofit savings compared to baseline. So here's your chance to add your 2 cents to the presentation. Give you another second to do that. And what we're seeing is 50% is kind of leading is the winner so far. 50% or more, 45% of the people said that, and you see the range. And I think that's one of our. I'm going to come back to this at the end of my presentation. Is what does deep mean, and what does it mean for our industry, and maybe what work do we want to consider doing in our industry to help define this more, because there's quite a range of answers that have come up. So let me start by sharing some definitions about energy studies and deep energy retrofits and deep carbon retrofits and the difference that we see between them. You know, we've seen out in the industry, and there's been a number of papers on DER, or deep energy retrofits. There was one a number of years ago from the US federal government case study, essentially focusing on larger scale upgrades, more than just a typical energy retrofit, significant reductions, extended return on investment. It's not a short-term payback in order to get there, often including more envelope and installation measures than you'd see in a typical energy study or retrofit. A deep carbon retrofit maximizes the energy efficiency, but it also significantly addresses the carbon side and reduces greenhouse gas and carbon emissions. And that's going to be one of the differentiating factors. And I'm going to be focusing on the DCR, the deep carbon retrofits, in this presentation in our paper. Now, you probably have seen different energy study comparisons, and ASHRAE has got a guideline. We heard about an updated guideline in this conference that's being developed right now. But I did a little comparison of energy studies, deep energy retrofit studies, and deep carbon retrofit studies based on my experience and what I'm seeing in the marketplace. And you can see the details here. Obviously, there's more in the paper that you can read up on. But just to give you a sense of the measures, the ECMs, or energy conservation measures or opportunities that are typically found in energy studies, at the bottom row, you'll find controls and speed drives, lighting and heat recovery. When you get into deeper retrofits, we're starting to see some redesign opportunities for HVAC. We're seeing envelope upgrades, often window installation, and you might start to see some of the PV and potentially even some demand response into that. Now, deep carbon retrofits, though, we start thinking more about fuel switching and electrification. Heat pumps, cogeneration, heat recovery chillers has been very popular in the last 2-3 years in our marketplace. Not so much on the on-site generation or the biomass heating, but you do see that in some of the deeper carbon retrofits. So one of our clients that I'll be featuring in the case studies had a very interesting scope of work for a DCR. And the first base level of work was a typical retrofit. What are the opportunities for the relevant systems that we're analyzing with a positive net present value? That was a restriction. Just, if it economically, does it make sense? The net present value is greater than zero, that's more of a typical retrofit. But they also wanted to see the technically feasible possibilities, and that was sort of the maximum energy and the maximum GHG savings possible to approach net zero energy and net zero carbon. And so we had the financial side in case one, the technically feasible in case two, and then they said, give us a combination of the optimized solution that will balance the positive NPV, the best ROI, but still trying to meet our carbon objectives. And you got that range. I thought it was a fairly interesting way of approaching how to procure and how to ask for deep carbon retrofit studies. And the other part that was very unique and interesting in this case was that the stakeholder engagement aspects was was definitely emphasized both early on, before starting, getting the stakeholders together in the room to define the DCR and the parameters, and also halfway through the project to check in on the findings and to see what makes sense and what doesn't. We learned from that process involving not just ourselves, but the owner and the facility managers and technical reps, and we even had some visitors and participants from the city of Vancouver. What we found was that the heritage aspects around a deep retrofit were really important. How you're going to impact the envelope, how far you can go with the envelope, and the brick buildings that we're looking at in some cases were more sensitive to heritage considerations. So the workshops were a really interesting part of the scope of work. Other considerations, just to briefly mention, is that, generally, you have a mindset shift that people aren't just looking at the quick payback, but really looking at their commitment to low carbon. And so that's what we're going to feature today in these case studies. And I think it's fun, not to have a whole bunch of slides where you see lots of text, but rather to see some practice. And so the nice thing is that I'll share with you 3 cases of projects that were that not only were studied, but that were built, and that we have the M&V post-retrofit. And so the studies start with one that's probably closest to my house in Kitsilano. This is a Kitsilano Community Center and an arena. And so the overview here is a great one because you get to see on the left-hand side, in terms of the site plan, the arena, pretty standard rectangular box there. And then more interesting, on the right-hand side, you see the community center that was built in phases with some additions. You have a weight room and multi-purpose rooms and the like, and community centers and gyms and so on. What you might not see clearly, but I want to point out, is if you look at the in between the two, there's actually a walkway that connects the two for shared services, so that you can go back and forth when we don't get a very harsh winter, but we do get a lot of rain. So you can make your way through from community center to arena via there. That was a very interesting feature for us because it allowed us to have a nice conduit to tuck our pipes up underneath that walkway to go from one building to the other as we went through this deep retrofit. And you see a number of images here about the community center. You're not looking at a very new building built in the 50s initially, and then renovations over time, in the arena in the 70s. But the retrofit strategy was quite comprehensive. The heat recovery was there, the conversion from essentially almost eliminating gas in the building, and going to heat recovery with a number of heat pumps. So we're going to show and share with you some of those pictures in greater detail. This schematic shares the picture in a more technical way for those that are more technically inclined. The yellow is the key, and the yellow line or orange line that goes between the rink and the community center in the schematic overlaps with that walkway that I mentioned earlier. And of course, some of the areas, like on the left-hand side, the ice in green, you see the ice plant compressors. Those are, if you had arrows to add to this diagram, you'd see those would be going downwards into this heat storage unit. And that heat storage unit we're going to come back to, going through actually, I'll just jump to the next one and show you a picture. So here's on the right-hand side, this heat storage unit. That's an external tank that we built that houses the heat. You need to be able to store that for when you need it. And on the left-hand side is the plate frame heat exchanger. So that would be what you'd see next to the ammonia condenser labeled on this diagram, and the heat storage is on the bottom left. And so you see the picture of that. We also see a boiler that is rarely used, but if the heat recovery is not available, you see a ring boiler that could add heat to the loop. And you also see the HRC for heat recovery chiller, both in the rink side and in the community center side. Now, if you're wondering about the temperatures, the red, 50 degrees C, so those of you that are south of the border, that's about 122 F, and the mid temperature, the yellow is at 20 degrees C or 68 F. That's transferring heat between the two. When the rink is shut down, which happens in the summer and happened during COVID, the heat recovery heat pump that's shown on the community center is able to generate heat, and instead of the arrows going up to the environment, then those arrows go down into that heat exchanger, into the loop, and that could provide heat for the whirlpool, the domestic hot water, and the heating system in the community center. In construction, the unique thing about retrofits for deep carbon as opposed to a passive house and new construction is the tight space you have. And so to get this heat recovery chiller into a confined space is not easy. So having the modular chiller come in and dealing with issues like vibration are so key. And so you see the tight space in this photo, you also get to see the importance of thinking about the zone level issues. And so this is a community center. It takes me back a number of years because my university age daughter was 3 or 4 when she had a birthday party in this room. And the top picture shows the traditional RADs, hot water RADs that were for high temperature. And so in order to accommodate low carbon heat pumps and electrification, because we have a very clean electrical grid, 95% generated through renewables, we're able to get the performance that we need, the heating that we need, by changing out the terminal equipment. And so the bottom 2 photos show a picture of the new slender and high surface area heat exchangers that were added to the multipurpose room. At the end of the day, it's nice to be able to look back, and this is one of the things I love about my job. Our team did an awesome job here, and the pre-retrofit 2015 is in green, and the post-retrofit in yellow is in 2019, and the actual results are showing 82% reduction in fuel. We have 3,800 gigajoules, and again, for those south of the border, it's about 36,000 therms, and we're on our way to go even further. The remaining gas, we're looking at how we can squeeze out the last bit by converting one of the boilers for the whirlpool even further. So the nice thing about this is we were able to combine efficiency and fuel switching so that the increase in electrical was actually minimal. For most months, we're actually seeing overall for the year, we saw a decrease in electricity as well, but most of the savings here is coming from the natural gas side. Comparing in the city of Vancouver, which has a greenest city mandate, the Kids Community Center in red was one of the medium to higher community centers with a rink, and we're able to get it down to one of the lowest ones. So it really jumps down, and you see that in the range from 53 kilograms per square meter per year to 11. So you can do those units on your own, but pretty significant reduction in greenhouse gas intensity, and really a project that really makes you feel good about making an impact. The second case comes from our federal government. It's the Pacific Environmental Science Center. It's on the North Shore and the North Shore of Vancouver, in the greater Vancouver area. And it has a bit of another story because of the complexities. This facility provides chemical, biological, toxicological analysis to support many department programs around the environment and climate change Canada. So the lab equipment required to do their work was very energy intensive, and they really wanted to focus on how to make a difference. So solutions that were here was that we replaced the hydronic heating boilers with dual return condensing boilers, really improve the efficiency. We upgraded the domestic hot water heating with new condensing water heaters, again, support for both of these from our natural gas utility, FortisBC. And we also looked at hydronic system and HVAC upgrades for optimizing efficiency. The solutions included lots of controls and control strategy. And on the chiller side, we're currently in the construction mode of adding a chiller system upgrade to an air source heat pump, which is going to be ready for 2021. Finally, what the client has done is they've looked at the option to purchase RNG, stands for renewable natural gas. So those are is natural gas generated through, in our case, a lot of agricultural sources. And there's a mandate that our provincial government has given to have the amount of natural gas hitting 15% by 2030 in the grid. So the overall results was a 33% savings, decrease in natural gas. We're planning to see that get to 46%, and then they offset all the remaining natural gas, and they have been with renewable natural gas. Our last of our case studies is a college. You see one of the older buildings in the college. It will have a lot of new buildings too. Not very unique names, but the A building was the first building built, and that's the one that we focused on. Newer buildings followed, including just the year before last, where the science and technology, the T building, was added. A lot of growth on campus. This A building was built in the late 60s, 50 over 50 years old now, and it contains more than 50% of the campus area. What we noticed was on the right-hand side, you'll notice the energy intensity. We refer to that as the Building Energy Performance Index, or BEPI. You might refer to that as an EUI. And the A building has both electrical in blue and gas in red as the highest, and it really cranked up the value for the campus. And so having what's referred to a shovel-ready project is really key, because there was some federal funding that was available if you were ready to build. And I think this is a good concept in terms of the green recovery being ready to go when it happens. And we were able to convert a constant volume system, 140 VAV boxes, replacing aged air handling units. We followed design considerations that are standard for what you'd expect in terms of ASHRAE 62.1 and 90.1. But what I want to focus on is the low temperature design. And what that's done for us is it's really enabled us to work on the next step, which is to allow for a low carbon heating plant retrofit, which is happening this summer. So the unique aspects that were kind of cool and innovative was the fan wall technology, also great for a retrofit, using smaller individualized fans as opposed to massive fans. Here we have 10,000 CFM fans. There's 7 of them. Lots of controls and commissioning were so critical and important. Air balancing were important, and you really get to see in the schematic here from the DDC system, those 7 fans there, and the amount of tweaking that we had to do, everything from finding leaky ducts because we weren't getting the air up to where we thought it would be, to tuning holistically to improve performance. It took 6 to 9 months really to make it happen. And I'm really pleased to be able to share that we achieved over 50% reduction, and by converting the heating plant to a low carbon plant over the next year or so, that will go even further. So another time for a question. Just give me one thought. I know we're a little bit tight. I'm going to give you sort of 30 seconds. And what's the first thing that pops into your mind of one thing that I've shared in one of these 3 case studies today that's the most impressive or informative that you want to learn more about or read more about or get more information? The one, maybe just limit it to 1 or 2 words. Take a moment and submit those right now, and I'll take a drink of water. So looks like I won't see those answers right now, but I'll get them after, and I'll be able to get back to you if there's a question that might have popped up. So we're still learning of how the poll shares stuff in the web in today's session. So that one you won't be able to see. In terms of lessons learned, I'll just go into my wrap up. Considerations for DCR, deep carbon retrofits. The ability to apply a carbon pricing policies to make the business case is so key. The City of Vancouver is using an internal price of carbon to make their business cases fly. They use that for both new construction and retrofits. Looking at asset renewal is so important. We're looking at things like when equipment is due to be replaced and how you can phase that in. That was really key for Langara, being ready to replace aged equipment and be able to take advantage of that asset renewal. We saw in the case of the federal building and the ability to engage stakeholders, having the initial workshops around carbon and bringing everyone's ideas of how to go further and how to pursue and push the envelope was so important. Enlisting specialized expertise, we found that it was amazing to have on our staff one of my co-authors of the paper, who was able to really get into the controls logic for the heat pump. We found that the heat pump wasn't performing due to pressure cutouts, and we had to work directly with the manufacturer to really adjust to make sure that we're getting the performance we needed. And that was really the theme. This collaboration and communication was so important. We had a client who was commissioning and testing the system on a daily basis, also co-authored the paper in the City of Vancouver case, the arena. Great to have the collaboration. And then the training and commissioning, it can't be understated, the importance of that. So, I have a recommendation to end. I sort of getting the 30 seconds here, and I'm going to ask you to say yes, no poll. Do you think that our industry needs a standard definition of scope for deep carbon retrofits so that we don't have all this range of answers? So what you saw earlier. So the question is there a need for industry to develop a standard for deep carbon retrofits? Yes or no? 5 seconds. So maybe you haven't answered, or maybe the poll's not working. I hope you are going to do that. Try one more time. Oh, 100%. That might be one person answering. If the poll's still up there, we encourage you to answer that. In summary, I want to thank Craig Edwards, City of Vancouver, Iram Green, and Sam Thomas from Prism Engineering as co-authors, who did a really wonderful job, not only on the paper, but also helping in terms of making these jobs get the savings that were happening. If you want any follow-up and any Q&A, obviously I'll be here. I'm interested to listen to my fellow Canadians on the eastern part of the country now, and we'll pass it on.
All right. Thank you very much, Robert. So yeah, from the eastern part of the country, from Montreal, Canada. So we'll be doing a presentation today on a new ESCO model for residential deep energy retrofits. Thanks a lot to the ACEEE and Panel 5 leaders for giving us the opportunity to present during this live session. It's really an honor. It's the first time myself participating in this event. We would also like to thank the town of Bridgewater in Nova Scotia, with whom we developed this new model that we're going to present to you today. So I'm Jean-Philippe Hardy. I'm a senior consultant at Dunsky Energy Consulting. As you can see, I'm accompanied today by Valérie Provost, who's a senior analyst at Dunsky Energy Consulting. Valérie has been deeply involved in the design of the model that we're going to talk about today. So a quick note on who we are. Dunsky Energy Consulting, we're a small energy consulting firm of about 35 professionals. We're entirely dedicated to questions surrounding the clean energy transition. As you can see here, we have three main areas of expertise: energy efficiency, renewable energy, and sustainable mobility. And we offer a large array of services around these three areas of expertise, from assessing opportunities offered by different technologies, measures, approaches, etc., to designing strategies to reach our clients' targets, and further down the road, evaluate the performance of these strategies and programs that have been deployed. And as you can see on the map, we have clients across North America. We're present in every Canadian province and territory, and we're active in about 15 states in the US. So let's talk about this model. So we designed this model to accelerate deep energy retrofits in the low-rise residential sector. We named this model the Community Energy Retrofit Blitz, or CURB. So the need for this model really comes from the fact that even though the residential sector accounts for a very large portion of the energy efficiency and GHG reduction potentials in North America, most jurisdictions don't see a lot of deep energy retrofits done in that sector. So we really need to scale up the number of deep energy retrofits, as Robert showed, in the commercial and institutional sector, but also in the residential sector, to reach our local, state, or province level, or even nationwide GHG reduction targets. So our concept is inspired by two models that have really proven track records in helping making deep energy retrofits more attractive to customers. The first one is the ESCO model that you probably know. This model has had significant success in implementing deep energy retrofits in the commercial and institutional sector, generating around $8 billion in revenue in 2016, according to the EIA. However, mainly due to high transaction costs associated with different parameters of the ESCO model and energy performance contracts, the traditional ESCO model isn't very well adapted to the small projects, such as the ones that are required to do energy retrofits in the low-rise residential sector. If we look across the Atlantic, in Europe, there's the EnergySprong model that was developed in the Netherlands. That is another source of inspiration for our model. So the EnergySprong uses a concept of highly standardized retrofit packages, and mainly comprised of prefabricated envelopes, HVAC components, and modular solar PV kits. These are combined with innovative financing to implement mass deep energy retrofits in European homes. Since its beginnings in 2013, so it's a fairly recent model, more than 5,000 homes have been retrofitted in the Netherlands under the EnergySprong approach. And many countries, including some states, Canada and some states in the US, have imported the model or are currently in the process of doing so. So our model really tries to combine the best components of these two models, of ESCO and Energy Strong, into one comprehensive approach with the objective of scaling up residential deep energy retrofits. Just a quick note on the fact that this model hasn't been implemented yet. As I said, we developed this model for the town of Bridgewater in Nova Scotia very recently, so it is still in the conceptual phase. And as such, jurisdictions who would like to implement this model or a similar approach would obviously have to figure out some of the details that we won't go into today. And of course, again, you have more details around the model in our paper. So this model is sitting on four main components, four pillars. The first one being a one-stop shop approach, which is very characteristic of the ESCO model. So this is really to make it as easy as possible for a participant to take part in the program, to ensure as much as possible a very seamless customer journey throughout the process. So the aim is to have a single point of contact for project design, financing, contracting, implementation, and even incentives applications. The second main component is the standardized process to expedite the projects, reduce transaction cost, design costs, and construction costs. And that aspect is very much in line with one of the main characteristics of the Energy Strong model. The processes themselves are highly standardized, but also the retrofit measures, which is possible because we're acting in the residential sector where there's much less variability in terms of opportunities for energy savings and types of equipment compared to larger buildings that typically need a much more custom approach. Third one is the financing component. So this one includes a long-term financing, which needs to be at least as long as the payback period to create a neutral or positive cash flow for the participant. And a financing component that includes that has no upfront cost for the participant and a very simple repayment mechanism. And the last one is guaranteed savings. So we have in our model, guaranteed savings are really built in the financing arrangement. And the associated risk for these guaranteed savings is managed first through a project aggregation, which is really important. So savings are not guaranteed at the individual building level, but for all the buildings participating in the program. And then the remaining risks are then shared between different actors, as Valérie will explain shortly. So if we go down a little bit into how this works, so this is a simplified process diagram of how the model works. So my colleague Valerie will go into more details about each part of the process, but let me give you a quick overview of the diagram first. So at the top, you have the blue squares, which represent the customer journey. So that customer journey, we want to be as simple as possible, as I said. Then just below, you have the orange. In orange, you have the ESCO side, so the point of contact between the participant and the program. Then in blue-green in the middle, you have the program administrator, who acts like a central hub for the program, kind of the quarterback who links all the pieces together. And then at the bottom left, in gray, we have the financing side of the program, providing the funds for the loans and also financially participating in the savings guarantee. So now I'll leave Valérie to explain each of these components into a bit more details.
Hi, everyone. So I'll just walk you through the process first. So imagine you wanted to renovate your home, and you would learn about this program that allows you to do all the work with minimal efforts and no upfront payment. Wouldn't that be amazing? And it's quite simple. You just go on a website or contact the ESCO to participate in the program. You then fill a questionnaire that ultimately allows the ESCO to determine which are the best measures to implement in your home. They then send you a proposal with a quote. You can review it with absolutely no obligation. If you agree with it, you schedule a meeting with the contractor to confirm the work. You will ensure to check in your home that there are no particularities that would prevent them from either doing the work or achieving the energy savings that they've told you about. If all is good, you then sign the contract, and then there's no more effort required on your end. It all gets processed and the workers go to perform the retrofits. And once everything is completed, you just start paying this one bill at the end of every month. The amount in this bill is basically the amount that you used to pay for energy bills in the past, except that this time there's a portion that is associated to your energy savings that's going to be used to pay back the loan that was initially used to pay the contractors and the ESCO. But all this is fully transparent to you, and basically you just pay that one bill every month with no worries for the duration of the contract. All this is possible because of the standardized service offering that's been put together between the municipality and the ESCO, which I'll tell you a bit more on the next slide. So as part of the design of the program, the municipality would need to issue an RFP where the ESCO would apply to eventually be able to offer the program. In this RFP, the ESCO would have to propose an approach to standardize 3 key elements. The first one would be around forms and contracts. So basically that would include the standardized questionnaire. Every participant has to fill to determine which measures will be included in their package, a standardized contract that gets pre-populated based on the result of the questionnaire, and a process to effectively submit all financial incentive applications for which the project is eligible. So it comes down to the minimal cost for the participant. Secondly, you would want to standardize the costs and measures. All measures would have to be have a predefined cost, which is based on a few parameters, which would allow the ESCO to automatically generate the code, and then also to standardize the loan amounts that you'll be eligible for and that will be pre-approved. Finally, you would have this energy savings calculator that would basically use some parameters such as the square footage of your residence, the number of occupants, past energy use, to determine what are the guaranteed savings for each measures that are proposed to you. Ultimately, this will be used to define the reimbursement period for your loan. It could also influence the amount you pay every month if you want the participants to be able to get a portion of the savings back in their pocket right away. Once the ESCO is selected and the contract has been awarded, the municipality would need to enter into negotiations to define the specific terms of the agreement. In these negotiations, financial institutions, program administrators, and utilities could also be involved and basically work all together to define what are the specific terms of the program that works for everyone. Now let's have a look at how the money flows between the different actors. Once the contract gets signed by the participant, the program administrator is going to review it to ensure it's compliant with the terms of the agreements that's been made between the ESCO and the municipality. If all is good, he then approves it and asks the financial institution to issue the loan. This loan is then used to pay the ESCO, who then pays the contractors to perform the work. Once all the work is completed, as I said before, you pay this one bill. And the amount of the bill is going to be adjusted to account for weather fluctuation, just like you would normally expect with your energy bills. If it's a colder winter, you pay a bit more. If it's a warmer winter, you pay a bit less. The payments goes to the program administrator, and he's going to use the money to first reimburse the utility or pay the utility bills that with the exact amount of your new consumption. And he's going to use the remaining amount of your payment to pay back the loan. This system of having this one single bill basically ensures that or guarantees that your energy savings are going to be enough to pay back the loan. When it's not the case, or if the savings are lower than what they would be expected, then that would trigger the guarantee mechanism, which I'll explain on the next slide. So the ESCOs are responsible for guaranteeing part or all of the aggregated project savings. And here the word aggregated is very important. because each participant will have a slightly different consumption habits, or each measure will perform slightly different in each home. And ultimately, statistically though, on average, all the energy savings should be achieved for the entire community, not specifically for each home, but really for the entire community. When you put it all together, the ESCO is going to guarantee the savings. The way it works is that the administrator collects all the payment and must be able to reimburse the loan with all the savings that each participant achieved. If the amount of energy savings aren't enough to cover the full amount of the loan, then the ESCO must cover the shortfall. The risk could also be shared between the ESCO and the municipalities. Typically, an ESCO would guarantee about 80 to 90% of the energy savings, but the municipality could then choose to cover the last 10 to 20%, which is basically the riskier portion of the savings. And the reason why they could consider doing that is because they have a vested interest in the social and economic benefits that result from these retrofits. And that can include reducing energy poverty, increasing property quality and property value, stimulating the economy by creating new energy efficiency jobs, and even meeting their energy, their GHG emission reduction targets. So for all these reasons, it might be interesting for the municipality to take a share of the risk and invest basically in helping its community to retrofit their homes and participate in these programs. So that gives you a good overview of what the program can do. I'll now pass it back to Jean-Philippe, who's going to conclude with how we've basically addressed each barriers, or tried to address most of the barriers that are currently preventing participants to do home retrofits.
All right, thanks a lot, Valérie. So as you've seen, our model addresses some of the larger barriers to deep energy retrofits in the residential sector. We're not presuming that it addresses all of them. For example, it doesn't address the split incentive barrier, and we would need to think of another mechanism in combination to take this one down. But it does take down some important barriers, and that's what I'm going to talk about now. So the first one, that's an important barrier, is the lack of access to financing. With our model, homeowners that participate in the program have very simple access to a non-secured loan that's basically guaranteed when they take part of the program and then when they're eligible for the program. So that's the first one that's really important. Then we have the second and third one, which we can combine, are the lack of time and the lack of knowledge or information about energy efficiency. We know that this is a big barrier. People don't know exactly what to do. And people are not specialists in energy efficiency, like most people are not specialists in energy efficiency. So these two are tackled through the one-stop shop approach. And under this approach, what's great is that you have an energy efficiency specialist that is guiding the homeowner through each step of the process and basically takes care of everything from designing the project, making sure that it answers all the questions from the participants, explaining what kind of retrofits are going to be done, what are the benefits, taking care of hiring the subcontractors, supervising the work, applying for incentives, and so on. So it's really a concierge approach that makes it a lot easier for the participant. And the last one is uncertainty. And that's another big one. There's a lot of uncertainty in people's mind, and for good reasons, about savings materializing or not after an energy efficiency project is done. And of course, when you have these savings guaranteed, that will go a long way, a very long way, into reducing this uncertainty and taking down this barrier. So I think you see that this model has the potential to significantly reduce barriers and really increase the uptake of comprehensive energy retrofit projects in the low-rise residential sector, and that is the objective. And as I said, that's really important to achieve the GHG reduction targets and the energy efficiency targets that our jurisdictions have. So that's it for our presentation. So thanks a lot for listening in. We'll be happy to answer any questions you may have during the Q&A. And of course, there's a lot more information in the paper that we presented. So thank you very much.
Okay, can you hear me? Can someone in the team chat? Nothing. Okay. Okay, great.
You're good. We can hear you, Heather. We can hear you.
All right, thank you. Awesome. All right, well, thank you very much, Philippe and Valerie. Next, we'll wrap up this with our final presenter, Jareen Ahmed from Southern California Edison. Jareen is a senior engineer in the Emerging Products Group at SCE, where he focuses on whole buildings and HVAC technologies. He's worked on energy efficiency, demand response, and distributed energy projects, and worked closely with regulators and manufacturers. He's a recognized expert in the field and a voting member of 90.1 residential buildings. He will explore variable capacity heat pumps for residential and commercial applications. All right, Jareen, it's all yours.
Thank you. Good day, everyone. Thank you to ACEEE for giving me this opportunity to share the paper that we had written. And so what I'm going to be talking about is a journey. This journey is with variable capacity heat pumps that Southern California Edison, along with other partners, have been involved in over a number of years. And when we started this activity in about 2006, I think it was mostly geared towards energy efficiency. But now we see that this product also has applications towards greenhouse gas reductions, as well as building electrification, and also providing this flexible technology. So what I'm going to touch on is touch a little bit about the drivers that got us to do it, talk a little bit about some of our testing that we have done, and also how this has resulted in what we call our market transformation to get some of these products into incentives, and also moving it towards code adoption. First of all, I'd like to just acknowledge my co-authors, Edwin Hornquist, who's with Southern California Edison, Carol In with Insight, and Martin Vu with RMS Energy Consulting. So going back to what I had said, what was some of these drivers? So we have something called the Big Bold strategy that was launched by the California Public Utilities Commission, and just the HVAC piece was kind of getting the efficiency to improve, and also to reduce heating and cooling loads. So that was the initial driver. And then came along some of the policies that led towards greenhouse gas reductions, AB 32, Senate Bill 1477, that's looking at, again, decarbonization in the building sector, and also the executive order that calls for zero net greenhouse gas emissions by 2045. So SCE's commercial sector. So I'm going to talk a little bit about the HVAC and how it kind of impacts some of this. As you can see from here, HVAC in the commercial sector is about 28% of energy usage, And if you look into the residential, it's about 14% or so. So yeah, there is an opportunity to kind of impact energy reduction, as well as, if you look at the other benefits, is also greenhouse gas reductions. So variable capacity heat pump. Variable capacity heat pump is not very new technology. It's been there, but what we have seen now is in additional benefits. Right, we already knew it had the capability to provide reduced energy and meet all the part load conditions. And along with that is also sort of a grid responsive solution, and we see that there is flexible applications on a need for energy or cooling or heating. You could utilize that, and also base it on what kind of and how much you need. So ultimately, it's using less energy, and also on a call for cooling or heating, you can utilize that product. And also, I should say, heat pumps, of course, can provide both heating and cooling. So from a utility perspective, we are looking at how can we influence the adoption of these technologies, and also reduce the timeline for adoption of some of these new technologies. And you can see from these curves that we have out there, it's a time and technology adoption. So if it's business as usual, it's the curve to the extreme right, which is in black. And then utilities, when they have incentive programs, they can shorten the time period and get technologies to be brought into the marketplace at a faster pace. And then, as I had said, I work in the Emerging Technologies program, and what we do is we try to even shorten the path. So we like to go ahead of the curve and try to have technologies evaluated and bring it into the market and into our incentive programs earlier. This is a little bit of a busy, but again, this goes back to the journey I was talking about. So we started on this technology about 15 years back, and as you can see, it went through several iterations. We looked at VRF systems, we looked at field tests, we looked at even trying to look at the modeling aspects. How can you model some of these technologies? And also looking at it from a climate appropriate perspective is to see what could be added on to these kind of technologies to make it even more efficient. And ultimately that led to certain incentives over time. So just touching on a couple of these projects, that this is a field testing one. And I should also say that the references for all these projects, the detailed reports is in the paper. So you can go to the paper and then select the topics of interest, and you can find out the references to that. So this is again looking at a rooftop unit, variable capacity rooftop unit. And long story short, after we do the testing, we found out that there was a reduction in energy, and it was about 30 to 40% in energy reduction. And these reports ultimately feed into our process of getting these approved through our work papers and getting into an incentive program. So this also talks about what happened when we had this technology as part of our incentive. And it resulted, it says, the reporting said VRF mini split, so I just put it out there as that, but it had to do with VRF systems. And it accounted for about close to 4% of our savings. And this is, again, just specifically to the VRF systems. I'd mentioned that we were looking at also looking at, I would say, how can we optimize these systems even further? And so we looked at testing different combinations and added an evaporative pre-cooler to a variable capacity package system. And we found out that there was additional benefit in reduced demand, as well as there's a potential for added capacity. This is under project that our codes and standards team was involved in, and you might have heard a little bit more detail on this topic, I think in panel 1 on Tuesday. I think John Proctor covered some of this. But again, this I think it goes back to what we had seen. It provides the comfort, but there was some challenges with the controls, and also I think along with that was, again, the design practices that needed to be so coming back to what we call grid responsive solutions, right? So when we started, we were looking at energy efficiency and controls, and it was looking at part loads. But the newer generation of variable capacity heat pumps can provide additional benefits. So, for example, they work very well in cold temperature conditions. You can eliminate some of the auxiliary heating devices, and also provide that flexibility and be also responsive, which is a little bit different from the traditional heat pumps that would not perform very well in really cold conditions. And also when it had some backup strip heat, the strip heat would come on during times when the power generation was considered to be not very clean. And this could also result in significant cost for additional grid infrastructure. So some of the recommendations, right, from the previous testing was how can you standardize some of the testing. There is a new effort going on, which is by CSA. It's called EXP07, which is looking at performance under part load conditions with variable capacity heat pumps. And also, I think some of the challenges that were found, is this control strategies that resulted in unpredictableness of the product. And also, I think we need to promote some of and educate on the right sizing and best practices. This is going back to some of our rebates that we had with VRF systems, and in the earlier stage, it was mostly commercial VRF systems that had the rebates, and you can see it's based on a dollar per ton incentive. More recently, we have rebates in the residential sector, and that's related to building electrification. So you have central HVAC systems. Sorry, this slide is a little bit, there's some overlap, but again, the first piece is talking about the central heat pumps. And and there's some incentives along with that. We also have it for multi-split systems. So in conclusion, so SE has been participation in carbon reduction. SE shared a white paper that they developed. It's called Pathway 2045. So it's more on power, clean energy and electrification pathway. That calls for, especially in the building sector, that calls for about 70% of space and water heatings in buildings to be converted to electric and clean energy sources. And I'm talking about this is California. We have been, as you can see, with this paper, we started this effort in 2006. So we would look into assessing new technologies and also developing best practices along with not just the design, but also installation best practices. And the SE's codes and standards team also worked on getting the compliance credit for variable capacity heat pumps in the past. And in conclusion, I think I would say they're bringing in the grid perspective, right? Along with the flexibility to utilize these products when and as necessary to manage both energy as well as demand and also customer choices. And so that's all I have. So thank you. And we'll move on to the question and answer session.
All right. Well, thank you very much, Shireen. I'm going to hand it over to Mikhail, and so he can get us started with our Q&A session.
Hi, it's Mikhail from Oak Ridge National Laboratory. We have lots of questions. We have, I believe, half an hour time for that, so let's keep track of the time. We can answer all the questions, or as many as possible. We start with the first presentation. This question is to Robert. As demonstrated in the Rink community example, is it easier to achieve DCR savings by expanding the scope, including a larger set of buildings? That is it better to collaborate than to go it alone?
And we considered whether we tie into there, and that would be probably one of the few options. Other than that, it's a pretty single-family home area that would be harder to connect to in terms of district energy. Now, I think it's easier. For the 2010 Olympics that were held in Vancouver, there was a community that was built for the athletes in the athletes' village, and the district energy system was developed using sewage heat recovery, wastewater heat recovery, and it was a lot more feasible when you're building the new buildings and all connecting to that system with heat exchangers. For us, the main issue was that there was a very good balance between the heat generated in the rink and the needs of the community center, and so we were kind of self-sustaining, and by adding the thermal storage tank, we're able to use the periods where ice is being generated and heat's being generated when you're making ice, and have that carry forward over to other times when you're not making ice. So we had a good balance, and we had limited size. We couldn't really have made the plants any bigger. You saw kind of the tight mechanical rooms in there. So in this case, it was a nice balance between the two, but I do see some cases where going bigger could be better.
Thank you. Another question for you. were these savings weather normalized?
Yeah, both the years that we actually wanted to make sure that we showed unadjusted numbers for the business case, especially for the case study, especially for those audience members that are less knowledgeable than all of us on the call about normalization and Q-sum and savings. So what we did is we did do a comparison that to 2015 and 2019, the 2 years had the very similar heating degree days, which is what the main driver is for fuel, and they were very similar. So it was a fair comparison, and that 82% figure is right. We did prepare, and we do have, for the client and more technically savvy, we do have Q-sums that are built on energy models that are created, and those are tracked on a monthly basis.
Thank you. Then there's a question about the overall BDU savings. What were your overall BDU savings, percentage reduction from baseline?
Right. Well, every case study was a little bit different. They all were, in that in excess of the 50% savings level. Each of those three has slightly different numbers. The rink example, the beautiful thing was, even though we electrified and went with the heat pumps, we did not see an increase in electrical use. So we saw the gas go down and not see an increase in electrical. I say, well, how can that be? It's impossible. The answer is that we combine efficiency and controls improvements at the same time, and by taking that holistic approach and also looking at optimization and in the rink side, we're able to achieve that. So it's nice to have that the year behind us. And I think the follow-up question on that one relates to the pandemic and what happens in terms of the scenarios. Well, the ice rink and community center have been, for most of the pandemic has been closed. I think the community center has limited operation right now. The rink, hockey is starting up in Canada again, and we'll see how many people. I know that depending on the jurisdiction you're limited on the number of players on the ice. In this case, I don't think this arena has opened yet. So I don't even want to say we'll see more savings, because I don't think that's a fair way of looking at it. But definitely, it was a self-financed project. All three of those were self-financed, and unlike the Dunsky examples where there was ESCO models, and the M&V is important to see the results and to prove the results, but not in terms of any payments or any participation in programs. So they were all based on calculated savings in terms of incentives and so on. So I think we'll be okay for that and have less complications than some others do. If you want, Michael, I can answer another question. It was around how long it took. This is kind of a sad story. The Kids Community Center took over a year to build, but it's because of a fatality that happened in a rink with an ammonia system in the eastern part of our province. And, essentially all work in ammonia plants were put on hold. And critical that we, safety first. There's actually a number of fatalities, unfortunately, in this rink. And so that definitely slowed down any work in the refrigeration plant. And once we got the go-ahead, and once public report was issued about the cause and effect, then we were able to proceed with construction. But it ended up taking over a year to do that.
Great, thank you. Since we are apparently ending at 2:15, so we have to move on to the next presenter, Jean-Philippe. There's a question: does the financing arrangement go along with the home if it's sold? Jean-Philippe?
You have to unmute yourself.
Me? I wasn't.
We're unmuted.
We're unmuted, but does it work?
Yeah, we can hear you.
You can hear me now? Okay. Strange, because I did unmute. Anyway, so that's a question we got a lot, and it's a great question. In the feasibility study that we did for the town of Bridgewater, we touched on that question briefly. We envisioned two mechanisms that could be that could happen when a home is sold. So the first one being the participant would have the option to pay back the entirety of the loan. So so the new homeowner doesn't feel like he's stuck with something he didn't embark on himself. So that would be the first option. And then obviously the new homeowner would pay the lower energy bills. And the second option would be to transfer the single bill to the new homeowner, which is in fact very similar to a utility bill. So we could envision some sort of mechanisms to make that one single bill payment transferable.
Great, thank you. Another question to you. ESCOs have primarily focused on low-hanging fruits, lighting and HVAC. How do you plan to increase envelope retrofits?
Yeah, that's a good point. Yeah, envelope retrofits are a real challenge because in a lot of cases, their payback period is much longer. However, here we're talking about longer-term payback periods, so we're not talking about 3-4 years payback. We're talking about more in the range of 10 to 15. And so we could, so under this type of, sorry, with a longer payback, such as 10 years or 15 years, we could actually aggregate, we could actually combine HVAC measures and lighting measures, which have much shorter paybacks, with longer term payback measures, such as could be attic insulation, could be window replacement. And so that's the thing. We could actually, by bundling all these measures together under a longer payback, we could push for more envelope measures to reduce the load.
Thank you. And one more for you. How do you handle increased energy use due to behavior changes or energy use increased by the customer not related to the retrofits? Is this a theoretical program or has it been proven?
Do you want to take this one?
So at this stage, it is theoretical. We haven't, it hasn't been deployed yet, like we said before. So it would be great to actually see it live in action to how it performs. But at the moment, I'll give the more theoretical answer. So around the risk of if participant increased their consumption, that's obviously a possibility. But we feel that if you aggregate all the savings, and obviously some people might increase their consumption, but there are some people that are very cautious too and are going to maintain their same consumption, same habits. So we feel that obviously there would be some safety factor included in the energy savings calculation, but overall within the community, we think it should balance out. And obviously for this to be statistically true, that involves like a large enough group for it to be possible. We're thinking in we haven't calculated that specifically yet, but we're thinking in the hundreds of participants. I guess the other aspect is that obviously if some people do increase their consumption, it comes back to what I was saying a bit earlier, that municipality might be willing to kind of support and cover this riskier portion of the risk because of all the benefits that can come out of these, I guess, retrofitting the overall park, building parks in their community. So it might be worth the cost to them for the greater good of the community to kind of take that risk and cover this risk if someone do increase their consumption drastically.
Okay, great, thank you. Next question to Jareen. Is variable capacity a designation in AHRI, or how would you determine from a spec sheet?
Can you repeat the question?
Is variable capacity a designation in AHRI, or how would you determine from a spec sheet?
Yeah, you can determine if it's multi-speed or variable speed. You can determine that. Yeah. So yeah, That's I have to look at a recent one, but yeah, you can. There's a way to determine that.
And then, okay. So what is the next question? What is the most simple and straightforward way to determine if installing a heat pump is appropriate for a building retrofit?
For building electrification, if you're replacing a fossil-fired, for example, a furnace with a heat pump, that is I would say building electrification.
Okay, thank you. Let's see. Maybe we are almost in the end of time. I'm not sure who this question is. This question for you. How does natural gas or natural gas efficiency play into this scenario, especially as it is relied on by many big and small communities such as low income? How does it play into the energy burden issue? Does it sound like that question is to you?
Is it to me or to Robert? I was not sure about that. So.
Yeah, could be. Doesn't say.
I can tackle a question while we're waiting to figure that out. I think that one might be Dunsky. There's a couple of questions about RNG. And first time I saw it on the bill, I was wondering what was going on because my initials are RNG. And I was wondering why my initials were on the bill and what was going on. But in reality, renewable natural gas is quite expensive. It's about 10 times the price. And so in a residential application, you can choose a percentage, and maybe 10%. And just like you'd have, PV added to the grid, the RNG is added to the pipeline network. And so you don't actually buy, the RNG from a farm. It goes into the distribution system, and you're allocating your part of that, and it's accounted for through that purchase. And so the question was, could you just buy all RNG? Was that cheaper? Well, I think in the long run, it's quite expensive from an operating cost perspective. Capital renewal and energy reduction. I mean, for me, I've grew up over 30 years now, and my practice is get rid of waste first, do your efficiency next, look at all the heat recovery you can possibly do, and then finally look at alternate supply. And if you have any extra, whatever remains after that, then look at your offset purchases to get you to zero. So, for me, the cost effectiveness, is from first to last. The first thing that you can do that's cheapest is to turn things off and get rid of waste. And the last thing to do is to look at your kind of offset and that range. And so I think you're going through this whole range of opportunities. And I think that's the philosophy that our client was taking as well.
Okay, great. Thank you. I think we are running out of time. We have a social hour in the end of the day, 4:30. So please look at the engagement hub for a link to that one, and we can discuss more about all the questions that we have had. Thank you, all presenters and the attendees, for participating in this conference today. I don't know if anybody else in the management wants to say some final words. Heather? I think we are in the end of the session. There's no, I heard we will finish 2:15, so we can continue in the social hour as mentioned. Please look at it in the engagement hub and join that event. Thank you, everybody.